already conductor, so what is the requirement of semiconductor then? And if you don't want to conduct electricity, there is insulator. What is the use of semiconductor? So basically we found that at when we are increasing the temperature, something different is occurring, due to which semiconductor can either behave like a conductor or it can behave like an insulator. Okay, that is completely it is completely proven from the theory as well. Okay, but that is something we are not really concerned with. Okay, we are having a different type of semiconductor, and before discussing them, okay, the base I have already discussed. Okay, if you want to just have a revision, then I will just let you know that basically when semiconductor was discovered, people started questioning that what is the use of this semiconductor, because at zero Kelvin, semiconductor was just like an insulator. People said that if you want to conduct electricity, you have already conductor, so what is the requirement of semiconductor then? And if you don't want to conduct electricity, there is insulator. What is the use of semiconductor? So basically we found that at when we are increasing the temperature, something different is occurring, due to which semiconductor can either behave like a conductor or it can behave like an insulator. Okay, basically in general, the conductivity of a conductor is the most, then comes the conductivity of a semiconductor, and then comes the conductivity of an insulator. Okay, and the conductivity of a semiconductor can be controlled by temperature and by doping. Temperature, I have mentioned that it can be increased or decreased, and doping basically means that creating some impurities there. Okay, but what is the justification for this? So by now we were just having the orbital theory. Okay, the orbital theory says that there is a nucleus, around that nucleus there is orbits, and in that orbit the electron keep on revolving. Okay, but there is also one theory which is known as band theory, which says that in an atom there are two kinds of band. One is known as valence band and the other one is known as conduction band. Valence band are the one in which the electrons are in the bonded state and they are not movable at all. But there is a conduction band which is at a higher energy level, and the electrons that are present there are mobile, they are free, and they are the one which are capable to carry the electricity. Okay, the gap between the energy gap between the conduction band and the valence band, that is known as a band gap. Okay, it is represented as EC minus EV max. Okay, I hope that is clear. Okay, now if I talk about conduction band for the if I talk about the band theory for metal, so you will find that at 0 Kelvin the bands are overlapping, that means the conductor is having maximum conductivity there. Okay, the bonded electron and the free electrons are all mixed together, due to which the conductivity is very high. As you will increase the temperature, randomness of electron will increase, therefore resistance will increase and the conductivity will decrease. Okay, so on increasing temperature for metal, the conductivity decreases. If talking about insulator, the band gap is more than around 3 electron volt, due to which at 0 Kelvin it is more than 3 electron volt. That means that the band energy is so high that the electrons are not mobile at all, because the electrons are only present in the valence band. No electron is present in the conduction band, due to which no electricity is being conducted through the conduction. Okay, when you will increase the temperature, the electrons, the bonded electron of the valence band will gain energy. They will just excite and they will go to the conduction band. They will conduct the electricity. So electricity is conducted by the electron which is present in the valence band and the hole which is created in the valence band. Let me repeat it. The electricity is carried by the free electron that is present in the conduction band, okay, and by the hole which is present in the valence band. Okay, so basically for insulator, increasing the temperature increases the conductivity. Talking about semiconductor, so for semiconductor the band gap is not too high. The band gap is almost like less than 1.2 electron volt, okay, in general. Okay, so basically when we increase the temperature, since the band gap is not very high, okay, I can say it is not very high, so electron hole can be created easily. Since electron hole can be created easily, more amount of electron will jump to the above state. Okay, hole will be created in the valence band, and therefore conduction of electricity is possible. So as you will keep on increasing the temperature, so with increase in temperature, the conductivity increases and the resistivity decreases. This is the net summary till this point. Okay, what I came to know from here, that I have terms which are known as NH, NE and NI. NH represents the number of holes. Okay, I am repeating it, not number of holes created. Ne represents the number of electron. Which electron? Free electrons that are created. Okay, and Ni represents the intrinsic charge. Okay, what are these intrinsic charge? Earlier in the valence bond, earlier in the valence band, the electron was bonded there. The electron was bonded to the hole. Okay, with increase in temperature, the electron just moved away. The electron just moved away, and hole is left behind. I hope you are getting this. So, what is intrinsic charge? Intrinsic charge represents the number of electron. Okay, intrinsic charge represents the number of electron that has been created, or you can say it represents the number of hole that has been created. Okay, in pure semiconductor, repeating this again, please mind it, that in pure semiconductor, the number of electron is equal to the number of hole that have been created is equal to number of intrinsic charge carrier. Okay, you can say that this is the most important key point, okay, in this lecture, that number of hole is equal to number of electron is equal to number of intrinsic charge carrier. Repeating this again, that there must be a correction, that it is not just number of holes, okay, it is number of holes per unit volume. Okay, please note this, that I have in a single go I can't talk about the whole conductor. Okay, let us say I have a piece of element, I can't talk about the entire element in a single go. Okay, I have to take every single unit and I have to talk about that particular unit. So NH represents the number of hole created per unit volume, NE represents the number of electrons that are created per unit volume, and therefore you can see that Ni represents the intrinsic charge, okay, which are present in per unit of volume. What is that? We will be dealing with it. Okay, I hope till this part there is no difficulty, no doubt. Is there? Okay, fine then. So yeah, this is something which I came to know. Okay. Okay. Well, if I take a pure semiconductor, if I say that I am having a pure semiconductor, so how will the current be carried there? Let us say I have increased the temperature at 0 Kelvin, this was behaving like an insulator. Now let us say that I have brought it to a room temperature and now I want to conduct the electricity. So how is the current influenced here? Okay, can you name any of the semiconductor you know? Okay, well, we have a lot number of semiconductor. If you remember the ladder of the periodic table, the bridge of the periodic table between the metals and the non-metal. Okay, well, if you remember that, you remember that the bridge was something like this: boron, silicon, germanium, arsenic, Sp, Te, and polonium. Okay, this is the bridging, this is basically the bridge. Okay, you can say that this is the bridge of semiconductor. Okay, well, I hope that is clear. So basically I can see that this is my periodic number 13, this is my periodic number this is my column number 13. Okay, 13th table, 13th column. This is my 14th, this is my 15th, and this is my 16th. Okay, well, that is true. So we are having this bridge in the periodic table which act as the bridge between the conductor and the semiconductor. Now my main discussion is about this only. Okay, you can easily observe from here that I can take any of the semiconductor. Let us take, I am taking the silicon. Okay, I am taking the silicon. So what is the key feature of silicon? If you remember silicon, Si. Okay, do you know the atomic number of silicon? Well, the atomic number is 13. Therefore if I write the electronic configuration is 14, 284. Therefore in the outermost shell, which is the M shell, it is having 4 electrons. Okay, so either it have to either it can nor it can transfer the 4 electron, nor it can gain the 4 electron. But yeah, there is something which it can do, that is sharing. It can undergo sharing of electron. Okay, so what is the thing here? Well, you will find from here that if this is my sample, okay, this is my sample, this sample will have silicon atoms. So let us say that these are my silicon atom. Okay, these are my silicon atoms. Just hold for a moment. Okay, so yeah, these are the atoms of silicon. Now they are bonded to each other. Okay, I hope that is clear, that they are bonded to each other. And how are they bonded? They are bonded by the sharing of electrons. Okay, got it, that they are bonded by the sharing of electron in this way. Okay, now wherever there is an electron, okay, that electron is basically in the bonded state. Electron in bonded state, that means it is something like this. Okay, the hole is present beneath and the electron is present above. Okay, if electron is somewhere freed, okay, the hole is left behind. So if I say that the sharing is done something this way, okay, the sharing is done something this way, what is the thing I can observe from here? Just hold for a moment. So okay, sounds perfect. Okay, so yeah, this is my sample. Okay, my sample of silicon sample. Now in the silicon sample, what I have done is I have connected battery, I have connected the cell, I have connected the battery. So you can see that this is the positive terminal. Okay, this is the negative terminal. Can you let me know what should be the direction of current? What should be the direction of current? So the direction of current is this way. Okay, this is the direction of my current. Now can you say that what if the direction of current is this way, what will be the direction of movement of electron? Basically, since what I have done, I have created a potential difference. This is having a positive terminal, this is having a negative terminal, which represents the potential here. Okay, that means this is at a higher potential, this is at a lower potential. So if there is a potential difference, what is over here? Okay, a force is applied due to which electrons are pulled there. Okay, a force is created due to which electron are pulled. Basically, if the potential is something like this, I will be saying that this is the direction of my electric field that is created. An electric field will be created, which is in this form. So this is the way of electric field. Okay, now this electric field will pull the electron, will exert a force on the electron. Let us say I am taking this electron. Okay, so what will happen here? This electron, the electron will be removed from here. Okay, let us say that the electron is removed from here and the electron will start moving in this direction. I hope that is clear. The electron will get out of this hole. Okay, and it will start moving in this direction. What is left behind? Can you make a guess? What is left behind it? Okay, hole is being left behind it. The hole is being left behind it. I hope that is clear. So let me repeat it again, that in a semiconductor, electrons are present there. Okay, since this is a semiconductor, I can guess that the electrons are basically the element or the sample is having the bonded electron. Okay, bonded electron means that there is a hole and over that hole the electron is present. Whenever I connect it to terminals, electric field will be created, electric field will exert a force, and that force will move the electron. That force will be exerted on the electron and the electron will get out of the hole. Okay, and it will start to move in this direction. So by this way, all the electrons will be moving this way. Can I say that all the electrons will be moving in this way? So if all the electrons are moving in this way, this will be the direction of current due to electron. This will be the direction of current due to electron. I hope you are getting this, that this is the direction of current due to electron. Now what is left behind? Just make a guess. What is left behind to us? That is hole. Okay, what is left behind is hole. What is observed? Okay, in clinical in experimental things, we observe that the hole is actually not moving, but it is having a virtual tendency to move. Okay, the hole is not moving at all, but it is having a virtual tendency to move. Okay, and now let us say that this is something. Okay, if this is in bonded state, I can say that this is neutral. It was having an electron which is separated. Now the hole is left behind. So if the electron is carrying the negative charge is taken out. What is left behind? Hole. And what is the charge of the hole? Definitely my hole will be positively charged. So I can say that hole basically represents a positive charge. What does a hole represents? Hole represents a positive charge, and it is observed that holes virtually tend to move in this direction. The holes virtually tend to move in this direction. So this is the direction of flow of hole. Therefore, this will be the direction of flow of current due to hole. Flow of current due to hole. So what is being observed here? In the sample, the net current. Okay, the net current is due to the current of electron and is due to the current of hole. Okay, let me write it for you. Okay, electron moves out electron moves out due to force exerted by electric field. Okay, created created by the terminals, created by the cell terminals. Okay, so electron moves out due to the force exerted by the electric field created due to the cell terminal, whereas holes created represents positive charge, that virtually tends to move. Okay, basically this is a hole. Okay, this is so logical that how can a vacant space move? But no, that virtually tends to move. Okay, which represents which basically shows the direction of current, which basically is responsible for production of the current, due to which a current is produced due to a hole, and the current is produced due to the movement of electron. Okay, fine. Now I am taking you out of this chapter and I am taking you to the chapter of current electricity. Okay, in current electricity, if I say that this is my conductor, okay, in this conductor there is a free electron. Okay, in this conductor I am having a free electron. I am just asking you that what is the formula of current for this? Okay, if it is having the charge density as Ne, charge density as Ne. Okay, this is my electron, this is the area in which it is moving, and let us say it is moving with with Vd represents the drift current. So do you remember that the formula of I was is equal to V now? Okay, if you remember VENA, which if I just replace it. Okay, if you don't know, the formula of current is represented as VENA, where V represents the drift velocity, E represents the charge of electron which is moving there, N represents the number density of electron, and A represents the area of the conductor in which it is moving. So I can say that the current due to electron is equal to NEEVDA. Okay, or I can write AVD. Okay, and what about hole? I can write that for hole the formula of current will be NH, the number density of the hole, into the charge. Now since it is exactly as charged as the electron, but just with the opposite side. Okay, electron was negatively charged and this hole will be positively charged. So NHE into area, okay, into VDH. Now what does VDH and VDE represent? VDE represents the drift velocity of the electron and VDH represents the drift velocity of the hole. Okay, therefore I net is equal to I of electron plus I of hole, which is equal to NEEAVDE plus NHE into A VDH. Okay, VDH. I hope that is clear. Okay, now what is the main thing I can know from here? That the number density of electron is equal to number density of hole is equal to number of intrinsic charge carrier. Okay, you know that number of since okay, this is for a pure semiconductor and I am talking about a pure semiconductor, so I can take number density out, charge out, area out. What is left is drift velocity of electron plus drift velocity of the hole. Is that clear? Okay, are you getting this? Okay, I hope that is visible. Okay, are you sure with it that you understood it? Of course you have understood. Now can I change it to, can I say that drift velocity is basically, the drift velocity is equal to mobility, okay, mobility into the electric field. Okay, I know this is something which comes from the topic of current electricity and you might have not revised it at all.
It's lack of personal attention. With one-to-one mentoring, every doubt is addressed, every concept is applied, and real improvement begins.